Dennis or
Yes.
Robbie, do you want to lead out?
Please, Brian.
Okay, very good. Well, welcome everyone to the Healthy Planet Action Coalition. We are delighted to welcome Dr. Greg Rao as our featured speaker for today's HPAC general meeting. Dr. Rao is globally recognized pioneer in applied carbon cycle research with over 4 decades of experience advancing climate solutions. He currently serves as Chief Technology Officer and co-founder at Planetary Technologies. Greg will correct me if I've got any of this wrong. And where he leads the development and scaling of ocean alkalinity enhancement, a promising approach for marine carbon removal. Dr. Rao is also a senior researcher at the Institute of Marine Sciences, University of California, Santa Cruz, and he's held research positions at Lawrence Livermore National Lab and at NASA-Ames. His work focuses on safely accelerating ocean's natural ability to absorb and store atmospheric CO2, a process with the potential to remove gigatons of CO2 annually. Greg's leadership has resulted in Planetary Technologies becoming a global leader in carbon removal, marine carbon removal specifically, using mineral based antacids, if you will, to enhance ocean carbon sink with rigorous monitoring and third party verification. The company's achievements include winning the X Prize for Carbon Removal Milestone Award in 2022, along with our marine permaculture, and most recently, $1 million carbon removal prize in April 2025, just a month ago, for its progress in scalable, verifiable, ocean based carbon removal. Greg is going to share the latest science, technology, and policy developments in marine carbon removal with a special focus on ocean alkalinity enhancement. He'll discuss insights from Planetary's field trials, advances in measurement and verification, and the global potential of ocean alkalinity enhancement to help meet our urgent climate goals. Please join me in welcoming Dr. Greg Rao.
Welcome.
Hi, guys. Yeah, this is quite a surprise. Having just learned I'm the featured speaker here. But anyway, I guess I know enough about this to answer your questions. And by the way, Brian, thanks for the introduction. You got it was very well done. However, I'm no longer a chief technology officer. I stepped down from that. I'm just a senior advisor now. And yeah, so you guys want to just tell me what you want to hear about. I assume you want to hear about planetary, or is there some specific aspect you want to hear about, or do you want to just ask me questions and I'll tell you what I can?
Yeah, we could have a conversation. That would be fine. I'm particularly interested. So much of this hinges upon, let's say, the techno-economics. But I think maybe before then, it'd be helpful for those who are less familiar with ocean alkalinity of the natural process of producing, I presume, calcium bicarbonate or other related compounds. And maybe we just have a really high level description of how it works. And then I think the techno-economics are really fascinating because that will determine, I guess, how we actually scale and make it
Yeah.
affordable.
But more
Well,
broadly than that, Brian, I think one of the introductory things is about the role of the Healthy Planet Action Coalition, and the HPAC supports a triad approach, supporting emission reduction, greenhouse gas removals, and climate repair, primarily through sunlight reflection. We've had a lot of emphasis on the sunlight reflection side, but not so much on the greenhouse gas removal side. And my understanding of our conversation today was that your role, Greg, as a leader of the carbon dioxide removal Google group, gives you a unique insight into the state of CDR and where it's at. So I think that broader question of where is CDR at, alongside your specific technical interests, and that broader question is both political and scientific, technological. So that's some of the framing of the conversation as I understand it.
great. Well, thank you for that that framing. And yes, I'm aware of all of those technologies. And yes, I've been very interested in CDR for many years and all aspects of it, but in particular, marine CDR and in particular, alkalinity enhancement as a role there. But given that none of these technologies have scaled so far, and we're still in sort of early days here, I have a very open mind about what the winning technologies are going to be, and I hope that others are in the same frame of mind, and that we should not prematurely select winners here, but just have an open mind and allow the research and data to speak for itself, and we move forward as aspects of this are proven and as the cost effectiveness is proven, et cetera. So that's kind of my philosophy here and mantra. And yeah, so what would you like to talk about, or do you want to ask me questions, or what do you want to know?
Just a really short abstract, I think, on how ocean alkalinity works, and then
Okay.
any high water marks in terms of your techno-economic
Yeah.
achievements.
Yeah, well, let me tell you why I'm interested in ocean alkalinity enhancement. First off, most of the carbon on the Earth's surface, not inside the Earth, but on the Earth's surface in communication with the atmosphere, is in the form of alkaline bicarbonate and carbonate ions, like something like 85, 90% of the carbon. It dwarfs any other carbon reservoir on the Earth's surface. So, number one, this apparently is Mother Nature's natural way of at least storing carbon. So right there, there's an advantage here in trying to convert any carbon we have into ocean alkalinity. It's something that Mother Nature already does, has done, and has done it for a few billion years, and has been very effective. And over time, actually lowering the atmospheric CO2 in the Earth's atmosphere, which of course, you know, past geologic time was much higher than it is now. And that's because of what we call weathering of alkaline rocks. There is a natural reaction between CO2, water, and alkaline rocks, which are extremely abundant on the Earth's surface. Most of rocks on the Earth's surface are alkaline. They are reactive with CO2 and water, although most of them are extremely slow reaction. So, and that's the problem here, is that it obviously cannot keep up with our raising of atmospheric CO2 in such a rapid manner. It's just swamped all these mechanisms, geochemical, biological, otherwise, of consuming this CO2 that otherwise will happen over the next, 100,000 years or so, but we don't have that kind of time. So point number two is there is this natural reaction between alkaline rocks and CO2 that is very effective over geologic scales of consuming excess CO2. So point number two is Mother Nature already uses this mechanism to do CDR, natural CDR. Then the question is, can we somehow speed this up? Can we somehow, given that Mother Nature will naturally consume all of our excess CO2, but unfortunately on very long time scales that aren't relevant to us, is there some way we can accelerate that process? So that is why I got into OAE. That's why I am in an OAE. And the question is, Brian, alludes to, is there some way we can cost effectively accelerate this process? And it does come down to finding cheap, abundant alkaline material that we can react with CO2 and convert that into bicarbonate and carbonate in the ocean. And that means finding, what we're doing is looking for alkalinity sources that we can add to the ocean, alkalize it a little bit, undersaturate the CO2 concentration in the surface waters, and then allow CO2 to diffuse in and consume atmospheric CO2. Now, there's another angle to that. There are large regions in the ocean that are supersaturated in CO2, upwelling areas, for example. Large chunks of the ocean are actually CO2 sources. And that's because deep CO2-rich water is being upwelled to the surface. That's where all the nutrients, upwelling nutrients for phytoplankton production, et cetera, happen. But it's also bringing up this old respired CO2 that's from biological respiration occurring at depth. So the other way that OAE can work is by adding alkalinity to these sources and thus reducing the natural emissions of CO2 from ocean to atmosphere. So it's not just necessarily just about carbon dioxide removed from the atmosphere. It can also be about reducing natural emissions of CO2 to air. In either case, you're reducing the CO2 burden in the atmosphere. So it works either way that you apply this. So the issue, it really does come down to, economics here. Are there cost-effective sources of alkalinity? I originally got into this thinking about how we could produce alkalinity from alkaline rocks, how we could convert alkaline rocks that are very slow in reacting, convert that into some sort of faster reacting alkalinity that would help us out here. And I, for some years, explored the electrochemistry route of doing this. It is combining electrochemistry and geochemistry to tear apart rocks, to extract their alkalinity, and to use that alkalinity for OAE. And also along the way, I was splitting. I was actually doing electrolysis, so I was generating hydrogen. And of course, if you do this with green electricity, you've got a green source, actually a carbon negative source of hydrogen. So with that idea, actually, that was the start of Planetary Technologies, although back in the day it was called Planetary Hydrogen because we thought we were going to be a hydrogen production company as well as an OAE company. Well, we explored the electrochemistry for a few years and discovered that the cost of this with the approaches we were using were going to be prohibitive. And yes, you can drive down the cost of this, but it's going to take some years, I think, to do that. And we didn't want to become an electrochemistry company. We really wanted to get out in the ocean and start doing stuff rather than developing the electrochemistry. So we abandoned the electrochemistry about 2 or 3 years in. And we focused on the idea of using waste alkalinity. There's a lot of industrial processes that generate waste alkalinity. There's piles of it around cement industry, for example. And so the focus has now become locating usable waste sources of alkalinity that we can use for OAE and finding ways that we can cost effectively apply that to the OAE approach. And that's more or less where we are now. We've identified a number of sources. This will get us probably, into the millions of tons of CDR. I think in the long run, it's not going to get us to gigaton scales. But what it will allow us to do is at least get experience in alkalizing the ocean, prove out that it works, test that it is safe and effective to do, et cetera, et cetera. And then my hope is that in the coming years, there are green ways of actually producing large amounts of new alkalinity that we then can scale to very large scales. So that's kind of where we are, and that's the strategy, at least my thinking on where we are and the strategies that are going to be needed to really get to big scales.
Sounds good. Thank you, Greg. Before we go to Greg Slater's question, I would like to ask you about the limitations to scaling being alkalinity supply, and have you investigated the use of red mud from the aluminum industry, which I've recently learned about here in Queensland.
Yeah, well, we're also learning about, various sources of alkalinity. Red mud is something I'm vaguely aware of. There are other sources of alkalinity. So all of this is certainly open to discussion. We do have to be careful about other elements, other things in this material, especially heavy metals, etc. So that is a limitation there. We're thinking about ways that if we have a dirty source of alkalinity, how we might clean it up in a cost-effective way. That's something we're getting involved in. But yes, there are waste sources out there, but again, we have to be careful that they are not going to harm the environment that we're trying to help, and that there is appropriate alkalinity in there to do this CDR. And the other dimension is, of course, transportation. We've learned that you can have a source in China and expect to do this in the UK. It's very expensive to ship, and it can be a very significant carbon footprint of shipping this stuff around because it is a lot of mass. So what's going to be required is locating appropriate discharge sources with appropriate alkalinity sources so that you minimize that cost, you minimize that carbon footprint. And I should also say that rather than us building pipes in our own pipes and doing new discharge into the ocean, we are piggybacking on existing discharges. And that includes wastewater and power plant cooling water discharge. So those are the two things we're focused on. They're already permitted to do this. And so what it allows us to do is not to have to get new permits. We can simply operate under the existing permits. Although typically, some additional permission is required because it is sort of a new thing, a new application, but it makes the permitting of this much easier if we can piggyback on existing marine discharges into the ocean.
Interesting. That's great. And on the way to Greg Slater's question, I'll just mention that seaweeds are fairly adept at bioaccumulating heavy metals, sometimes 10,000 to 1 relative to seawater. But that's an interesting R&D question. Over to Greg Slater and then Peter.
Thank you. One simple question. You mentioned you foresee scaling to I don't know, hundreds of millions of.
Well, let's say a gigaton. Let's say a gigaton
Okay.
of CO2 a year.
Okay, a year. It was the yearly thing. That was a year per year. Okay, that's good. And then the other question, which is a societal question, is that why is all the money and attention going to direct air capture? I mean, you're talking, if you include David Keith's thing, that's $1 billion right there. I mean, why you're in charge of the carbon dioxide removal? You see all these guys. How do you understand why there's virtually no awareness of anything but direct air capture?
That's a very important and interesting story, and I've lived that story for about 2 decades now. And I'll just give you I don't know, maybe it'll be a longer story than I hope, but it really comes down to the oil companies wanting molecular CO2. When DOE first got into carbon dioxide management, there was a whole range of ideas on how to reduce emissions from emissions. And in the course of evaluating all this, this carbon capture and storage, CCS, came to the fore. And a big reason why it did was because the oil companies were, of course, doing EOR, enhanced oil recovery, with molecular CO2. They're familiar with doing that, and therefore any mitigation technique that generates concentrated CO2 is a potential huge advantage for them. Therefore, they unleashed their PR, their lobbyists, their entire mechanism to make sure that any government funding going toward technologies for emission reduction and then later, air removal, made sure that the public monies, the incentives, the tax incentives all went toward this approach, making molecular CO2. And that is why, to this day, those approaches have enjoyed billions of dollars in funding, and why they have such a public presence, and why it dominates the discussion.
Hmm. Does that mean 45Q and 45X does not apply?
Yes, it does.
It does
Yes,
apply.
it means yes. Those are huge incentives.
Right.
Can you imagine the CDR community if they said they made that tech neutral?
Mhm.
Just prove that you've absorbed CO2 out of the air and we'll give you billions of dollars. Can you imagine how far along the CDR R&D would be today if that happened?
So this sounds like another case of regulatory capture.
Yeah, it is capture is what it is. Yeah, it's not only carbon capture, but it's mines and tax dollars capture.
Amazing. Peter?
Great, Greg. Well, uh, it's a great, Greg. It's great to talk to you as always. Uh, I think you and I first talked in probably 2012 or something, uh, trying to figure out how can we remove 1,000 gigatons from the air. So it's just great to be face to face with you again. A couple questions. My goal, I think everyone's goal is to give our children a safe CO2 level like we had, which means removing 1,000 gigatons over 25, 35 years, or about 50 or 100 gigatons per year. And uh, when I look at the economics of it, I figure no one's going to be able to spend more than the Pentagon budget, or about $1 trillion a year. That's sort of the top ceiling for something which offers no immediate benefit to people, for our kids, but not to industry, not to warfare, and so on. And so if a tenth of that is pretty reasonable, 100 billion dollars a year, we could definitely pull that out globally. And if you have to remove 100, if we have a budget of $100 billion a year, we have to remove 50 or 100 billion tons a year, that sort of divides into $1 a ton if we're actually going to uh, actually get the job done. And it was just sort of confirming what everyone's saying, that the direct air capture, which is 1,000 times that, is a little bit off the mark. Um, First of all, does that calculation make sense to you, that if we're actually going to do it at scale, we're going to have to find ways that are $1 a ton or less?
Well, that would be great if we could find that. I guess at this point, I think it's unlikely that we're going to find that, but we'll never find it unless we try. So,
Yeah,
uh, great. If we can get it down to $1 a ton, yeah, I'd say we've pretty much solved the problem. We're not there yet, as far as I know, unless you guys know something I don't. But certainly our company isn't there yet, and it costs a lot more than $1 a ton right now. But
right.
let's keep trying, and certainly the costs will come down. And in the meantime, let's also put a lot of effort into trying to reduce our emissions, because clearly that's the easiest way to help us manage the atmospheres. Let's not put it up there in the first place, because we all know that it's not easy to get out of the atmosphere once it's there. So,
Yeah. I think the
but
three legs of
Well,
our climate
well,
triad.
so the second part of my question is well, with ocean fertilization, looks like it can do it for around that. The amount of iron needed is at most 40 cents a ton of CO2 removed. But that's a whole different topic. which we can talk about another time. When it comes to alkalinity, what are the cost constraints? Because there's transportation, there's grinding. Can you like summarize it in a few bullets? The
Well,
costs?
yeah, it's not free. There are costs involved in all those steps, transportation, processing, if you need to do processing, dosing, monitoring, all of that has costs and a carbon footprint. So all of that goes into our economics. And yeah, it's not cheap to do all that. And we're probably at the couple $100 a ton stage now. Maybe not quite there, but we're pretty close. So that's sort of our cost now or very soon. Again, that's very geographically dependent, et cetera.
Great.
Yeah.
Okay. Good.
Does that
That's a good perspective. And then you mentioned that upwelling water is sort of super saturated in CO2. Can you give a couple sentences about why the deep water is so rich in CO2?
Well, it's because of the biological carbon pump. You're producing organic matter in the surface that dies and rains down into the deep ocean. And of course, the microbes there need a substrate to operate on. And here's all this rich, juicy stuff falling down from the surface. So they gobble it up. And that's why a teeny tiny fraction of whatever is produced in the surface ever naturally actually gets stored in the sediments. And that's why the biological pump is so darn inefficient in storing carbon over long time scales, is because you got all this respiration going on and all this loss of organic carbon and conversion to CO2 happening in the deep ocean. So, of course, when any of this deep water gets to the surface, which it does in upwelling situations, uh, you release all this CO2. Now, on the good side, yes, you also release all the nutrients that those bugs have mined out of that super rich organic matter. All the nitrogen, phosphorus, all the other goodies have now been converted at depth to all these inorganic fertilizer, if you will. And so that's a good thing for the surface community, because then that upwelling brings all this nutrient-rich water to the surface. But all of that is due to all the respiration, all the heterotrophic consumption of organic matter happening at depth, and then the result of that, CO2 and nutrients, then coming back to the surface.
So that would be a result of enough oxygen reaching those depths to
Yeah,
allow.
it has
Yeah.
to be oxygen fueled, and if you run out of oxygen at depth, then all of that more or less stops. Now, of course, there's an anaerobic respiration thing that'll kick in when that happens, but my understanding is that it's very inefficient and not too effective in recycling nutrients. And that's why I think those advocating a biological pump for doing CDR need to be big fans of anaerobic death zones, because that's where you need to deposit your organic matter. Look for areas in the ocean that are already dead, that are already anaerobic, and you put your organic matter in there, and it's going to actually last. And maybe you won't have this loss of organic carbon and this regeneration of CO2 that you would otherwise have in an oxic environment, which is most of the ocean.
Yeah, Dennis and then Jonathan. Oh, yeah.
Right. Thank you, Brian. Very, very interesting to meet you, Greg. And my question has to do with the ecosystem of the current industry with alkaline sources. I was just wondering, what are your company's current revenue sources now and in the pipeline? And maybe it'd be interesting to share a bit of what other companies are out there in that ecosystem and how they are interacting with each other.
Right. So our revenue is strictly from the sale of carbon credits. There is a market out there, a private market, voluntary market, I guess it's called. And there are buyers who are interested in buying carbon credits that we're generating. So right now, that is the source of revenue for us. Now, remind me, I think there's a similar mechanism in the government that they're starting to get a carbon market, at least in the US, going a government carbon market equivalent to what's happening in the private sector. I'm not so sure where that is. We're not plugged into that, at least not yet. But right now, all of this activity is being fueled by certain companies and consortiums of companies like the one in Frontier, which is a large consortium of companies that are interested in buying carbon credits to offset their carbon emissions.
Mm-hmm.
So that's really what's fueling our company and other companies in this sector right now.
Jonathan and then Robert Chris.
Hi there, thanks. I have a low technology question. Obviously, some minerals are excellent at doing the chemistry, but in general, the coastlines of the world are generally bordered by rocky features. And what would be the efficiency of people who simply live near the coastline in unpolluted areas, not next to an oil refinery, but in a fairly unpolluted area, just taking material out whenever they go out into the water for fishing or whatever, and just dumping it in, whatever soil and rock happens to be available at that point. In other words, is there a general efficiency for the average type of rock and material in doing this, or do you have to get those high efficiency chemistry items into the water?
Well, for most natural materials, the reaction rates are very low. Now, there are companies that are adding rocks or minerals from rocks to the ocean, sort of more or less as is. There's like this green sand. Vesta, for example, is doing this olivine rock addition or sand addition to the ocean. And they apparently have a way of measuring how much CDR they've done. Certainly in those instances where it's very slow to happen, it's very difficult to verify how much carbon removal you've actually performed. So yes, private citizens could go out and throw rocks into the ocean, but how would you verify how effective that is? And of course, you always run the risk of whatever they're throwing in there has other nasty stuff in it that actually impacts the ocean in a negative way. So we have to, if we're going to put stuff in the ocean, we have to be careful that it's not hurting the ocean and that it's actually effective in doing what it is we want it to do. And I think that's a concern by just general citizens taking stuff and throwing it in the ocean without following up what actually happens or checking on what it is they're actually throwing in there.
Sure.
Chris, and
As
then
a
Robert.
follow-up, the natural process of heavy rainstorms and flooding washes whatever's on the surface into the ocean. There's a cascade of things that are uncontrolled. The idea that we also add to that cascade doesn't seem to be a great danger, given what is already running off of the continents and the rivers and stuff.
Well, again, we can try to speed up what nature is naturally doing, but we do have to be careful about the consequences of doing that, which may not be always a positive. So I would just caution here that we have to be careful about trying to magnify what nature's doing, because we may not do it in the exact same way. We may actually exacerbate impacts from doing that. So I would be careful about, again, adding stuff to the ocean without first testing it out and proving that it's going to try to do what you think you want it to do, in this case, to consume atmospheric CO2.
Thank you. Robert Chris, then Robbie Tulip.
Right, yes, really interesting topic this. I'm conscious of the fact that the climate system is a deeply interconnected
A little
system.
bit louder, Robert Chris.
Right, hi, is that better if I speak a little bit clearer? Oh,
Yeah.
I'm moving the machine up. Can you hear me better now?
Yes. Just speak
Fine.
slowly.
So I'm very conscious of the fact that the climate system is a deeply interconnected system, and the global warming is primarily caused by the carbon dioxide in the atmosphere, not that in the ocean. So we need to understand, as we are doing this marine carbon capture, what the impact is on atmospheric carbon because of the quite substantial transfers that continuously go in both directions between the atmosphere and the mixed layer, particularly. And we know that over several decades, despite the huge increase in anthropogenic emissions, that the airborne fraction has remained more or less constant, sort of 45 or 50%. Do you have any authorities or evidence or thoughts, insights into how the atmospheric carbon, and particularly the airborne fraction, is going to change in response to very substantial quantities of carbon capture, particularly in marine carbon capture?
Yeah, well, of course, the plan or the idea is that we increase the net flux of CO2 from the atmosphere into the ocean, and therefore reduce the CO2 burden in the atmosphere. Now, in doing that, in actually doing any CDR, we have to be aware that once you start reducing atmospheric CO2, that there's going to be a rebound from reservoirs that are already storing this carbon that's been absorbed, and in particular, the ocean. The reason the ocean is the main reason the ocean is a carbon sink right now is because there is this higher PCO2. There's a CO2 gradient, pressure gradient. There's a higher pressure of CO2 in the atmosphere than in the ocean, and therefore that gradient drives in CO2. So that's a good thing from an atmospheric burden point of view. It's not such a good thing for the ocean because it acidifies the ocean. You're putting additional CO2 and you change the chemistry of the ocean, which is not a good thing. It's also not a good thing because then if you, by some mechanism, you're able to lower that partial pressure of CO2 in the atmosphere. For example, by direct air, let's suppose we had a global direct air capture thing, and we've reduced the CO2 in the atmosphere to the point where now the ocean actually has a higher partial pressure than the atmosphere. You've then got this degassing going on, and that has to then also be consumed. And the thinking is that for every ton of carbon that you remove from the atmosphere, you're going to get back something like a half a ton or something like that because of this rebound effect. So that does make the CDR effort that much harder because storage currently is so leaky. It's not, much of the storage is not secure, and this can degas and come back out of storage once we start really significantly drawing down atmospheric CO2. So that's something that folks in the CDR space are aware of, and yeah, we have to account for that in terms of our efforts to try to actually reduce the burden in the atmosphere.
So when you talk about the cost, X dollars per ton for removing the CO2, is that the gross removal or the net removal? Because
Yeah, right. Yeah. Well, very good point.
Double cost.
Yeah, very good point. Yes. Right now, this rebound effect is not part of the voluntary carbon market calculation. Certainly, we're a long ways from having the ocean having higher PCO2 than the atmosphere. So for right now, that effect has been discounted, as far as I know, by the voluntary carbon market. But air-sea gas exchange is still a very big deal for MCDR because it is one thing to obviously remove or transform CO2 that resides in the ocean. It's another thing to then have that reduction in PCO2 in the ocean translate into a transfer of carbon from the atmosphere to the ocean. That's actually a very slow process. And if we had a super shallow ocean, it wouldn't be a problem because all of our alkalized water, all of our undersaturated water that we've created would eventually equilibrate with the atmosphere, and we could count all of the alkalinity, all the undersaturation we've created. We can actually equate that to an uptick from the atmosphere. The problem is the ocean isn't a shallow pipe pan; it's very deep. And while we can consume CO2 in the surface waters and undersaturate it, because of ocean circulation and motions of the ocean, some fraction of that undersaturated water isn't going to stay at the surface. It's going to be subducted into the deep ocean. And once that happens, it's out of communication with the atmosphere and may not see the atmosphere for another 1,000 years. So a lot of the accounting that we're going through and others in the MCDR field is to account for this inefficiency and this fact that not all of our alkalinity and not all of the undersaturation that we're generating is going to result in an immediate drawdown of atmospheric CO2. And this has become a big deal in the MRV for what we're doing and what should everybody else should be doing in the MCDR field is that there is this inefficiency due to the slow air-sea gas exchange and the mixing of water that we're affecting into deeper water, which will not contact the atmosphere.
Does it follow then, just to complete this understanding here, does it follow then, Greg, that the global surface air temperature, the GSAT, impact of MCDR is less than atmospheric CDR? Is my question clear?
I'll just
So removing
comment
removing a ton of carbon from the ocean is not going to deliver the same surface temperature reduction as removing the same quantity from the atmosphere.
That's true in the short time frame, in human relevant time frames. Now, if you have 1,000 years to perform this, in theory, all of that alkalinity, all of that undersaturation will ultimately see the surface. And if you're dealing in geologic timescales, no problem. It's 1-to-1. But obviously, for our interest, we need this to happen in a year, 10 years, 50 years kind of thing. And all we're acknowledging is that what we do and others do in the MCDR field is unlikely. It can't be 100% efficient because of this circulation, subsurface circulation, and the slow air-sea gas exchange.
Yeah, and one point of clarification, Robert, is that whitecaps and bubbles accelerate air-sea gas exchange. And what occurs in the top 10 meters, you commonly have a time scale of days for air-sea gas exchange. And it goes to weeks in the intermediate layers, let's say the top dozens of meters, and then annually in the mixed layer. The mixed layer, by definition, is the layer that overturns annually. And so you get this air-sea exchange occurring on those timescales. And I believe, correct me if I'm wrong, Greg, but Planetary is putting their alkalinity in the mixed layer and not below the mixed layer, would you say?
Oh yeah, yeah. We and others, it's very important that our alkalization occurs in surface waters
Great.
because if we put it in subsurface waters, we're screwed in the short term. Now, if you've got 5,000 years to absorb CO2, no problem. But if you want immediate or near term CO2 absorption by the ocean, your consumption of CO2 or your transformation of carbon dioxide that's in the waters has to happen, near surface and in short time scales. And as I said, there's this constant down mixing of at least a fraction of what the chemistry you've affected. And once that gets away from air sea contact, then it could be a very long time before the total CDR that you're trying to do is actually affected.
Are there,
Actually,
that's my last question, just to get to the bottom of this. Are there accepted algorithms that link numerically the quantity of MCDR with the surface temperature impact in the same way that there is for atmospheric CDR?
well, I don't know that there's a link to the actual temperature, but there is a link to the impact on atmospheric CO2. They've done global mapping of this
Mhm.
efficiency, specifically for OAE. There's this modeling group, Seaworthy, Mike Tyka, et cetera, who've published. It's actually an online, I think Carbon Plan has this online where you can go to any point in the ocean and see what sort of efficiency you can experience if you were to alkalize the surface ocean at that point. And you can see the trend, how much um, how close, what would how does the efficiency line look over time, let's say over the span of a year or 2 years or 10 years at any given point in the ocean? So that has been modeled. Now the impact on ocean, on atmospheric temperature, then you'd have to have a link between what atmospheric CO2, the relationship between atmospheric CO2 and temperature. Now there are those graphs that we've all seen that link atmospheric CO2 to temperature. So in theory, you could then convert this modeling that's been done just for CO2 and convert that into some sort of effect on temperature. But I don't think that's been done so far.
Is that data you refer to, are they aggregated at global scale, or is it all
Uh,
localized?
It's a global scale. It's sort of gridded global scale. And you can go to any one of these little grids and it'll show you the graph of the anticipated sort of time course of uptake of CO2 over time, given the inefficiencies that are involved, and
Great.
particularly the air-sea gas exchange.
If anyone
I
has,
could give you the link, Robert, if you're interested.
Yeah, could you put it in the chat? That'd be great if you could.
If I can find it right now, yeah. Otherwise, I'll put it in an email.
good. Thank you.
Carbon Path, I think it's Carbon Path who published that.
Carbon plan, yeah, that's right. Yeah.
And Plan, not Path. Okay, very good.
Carbon Plan. All right,
Thank you very
Robert
much.
Tislip and then Greg Slater.
Excellent work, Greg. Thanks so much for joining us. What I'm really interested in is the sequencing question. Like we're seeing global warming accelerating, and like as emissions have accelerated, so too has temperature rise. But it seems that the temperature rise is primarily due to feedback processes within the albedo processes, like loss of clouds and snow and ice and aerosols. And one of the big questions that I have for not just CDR, but greenhouse gas removal more broadly, especially methane, is the worry that this darkening of the world, this acceleration of the loss of albedo, is going to produce feedbacks in the CO2. Like for example, we're seeing methane from natural sources just accelerating. And so I'm really interested in your perspective on how the albedo restoration, sunlight reflection space links to your work on carbon dioxide removal.
Yeah, well, I am a supporter of geoengineering, SRM, solar radiation management. I'm obviously not working in that field, but I think we've come to a point where we have to seriously think about, direct thermal management of the planet. And so I'm very supportive of R&D in that area. I can't offer you any advice there. I think it would be very cool if somehow you could link the two. And in fact, an argument has been made by Keith that actually there is a carbon benefit to doing SRM by cooling the planet. There actually is a reduction in respiration, and I can't remember the full argument, but there is a linkage there that by doing SRM, you will benefit the atmospheric CO2 burden, but maybe not as directly as you would if you were just doing direct carbon dioxide removal. But I'm not sure what your question is, but certainly I'm supportive of investigating SRM, and it'd be very cool if there's some way to link SRM with CDR.
Yeah, that's what I was interested in. Just how you, and I suppose it's this sequencing question that the urgency of SRM is something that needs to be recognised as something that has to happen alongside the the CDR work. Like we've seen, for example, with the IPCC, that there's a suggestion that any work on SRM could be significantly deferred, but I think that's a very dangerous approach.
We need to start R&D right now on SRM, and it should have been started a long time ago. And all this pushback, I think, is unwarranted. I think there are ways of safely researching this that need to be explored, or at least we need to be having that discussion. How do we safely do SRM R&D? I think there are ways that we can do this, and we need to get on it. And I'm concerned that we're going to get to a point where we do need it, and we haven't done the necessary work. We then go at it in a huge way, and we don't know how to do it properly, and there's huge mistakes made, and there's more impact than benefit and resulting. So I think it does need to be taken seriously, and I support R&D in that area.
So, like that work that you mentioned from David Keith about how sunlight reflection could have significant benefits for carbon dioxide removal, that's contradicted by the sort of naive assumption that if there's less sunlight, then there's less photosynthesis.
I don't know what all his it's been a while. I may have just skimmed his article, so I don't know all the mechanisms he explored. He was the first author on it. It's not that old. I think it's, I don't know, 2019, 2018.
Yeah, I have seen that work, so I'll look it up again. Thank you.
Yeah, look that up. I'm kind of curious now too, because as you say, if you're reducing sunlight, then in theory you're reducing photosynthesis, so you should have less carbon uptake. But he makes arguments about respiration and other things that he seems to think it would have a positive impact on reducing the CO2 burden.
Okay.
Plants are not light limited. They tend to be water limited or nutrient limited. And because they're not limited, then, plenty of plants grow beautifully in cloudy conditions. And that's like 10 times less sunlight than you have under sunny conditions. So they're used to that. Anyway, Gregory Slater and then Dennis.
Thank you again. Just a couple quick things. Could you possibly share, you said your revenue comes from voluntary credits. Could you could you tell us how much you pull in each year? And secondly, this discussion of the rebound effect, which lessens the efficiency, is do the IPCC models take that into account in terms of their projections of the CO2 decrease that they make and publish?
Well, they're certainly aware of the rebound effect. It's in some of their reports. Now, whether they take it into account in all modeling, I don't know. But certainly that's one place you will find the discussion of this rebound effect. So I haven't read those reports in enough detail to know that if that's taken into account in all their scenarios. I don't know.
Mhm. Dennis, and then
Yeah, I don't know if you're willing to, but could you share your revenues? Right. It's okay if you don't want to share it.
I actually don't know what they are, but I would guess it's in the maybe hundreds of thousands of dollars.
Per year. Okay, so I mean the reason
maybe even
the
million.
reason
I mean, made deal. See, the other issue here is delivery. Often what happens is there's a pre-sale. They will give us money in order to deliver credits in 2027, 2029, 2030, etc. So there is revenue that we get that then we have to deliver on over a scheduled period. That's typically the way it works. And so, there are deals that are made for millions of dollars. I think we've made some of those.
But you'd have to spread that out over time.
Yeah, we have to spread it out over time. And of course, we're not making money yet here. It's a net it's a net expense right now. It's not a money-making operation.
I mean, my interest is just for all these different methods, how the funding looks like, and so
it's difficult. It's very difficult, and right now it's mostly it's mostly driven by these wealthy companies that want to reduce their carbon emissions through these offset purchases. Ideally, what should happen is government should be funding this. Government should be fueling all of this, or there should be huge tax incentives, et cetera, fueling all this. Well, that's not happening. So in the absence of that, we and others are totally dependent on this voluntary market. And in some cases, philanthropy. I must say, philanthropy has been a major help in terms of funding of getting MCDR off, launched here. And like Climate Works and others, they were really, really key in, I think, launching the MCDR field in the absence of government funding and other private funding. So that's another avenue of support that has been very important for what we're doing.
All right, thank you.
Great. Chris.
Yeah. Sorry, I was going to come back on Dennis's first point. That's now just escaped me. Just sort of wonder if you could remind me, and then I'll make the point. What was your first part of your comment?
Dennis?
Are you referring to my first question?
Previous comment.
Yeah. Yes.
Yeah. Yeah. Well, in fact, I was going to dig a little further into that issue of returns to the company on carbon credits. Maybe I could do that, and then you could follow.
No, that wasn't the point. It was the earlier point you made before that, before you got onto revenues and things. So you made 2 points.
Oh, well, I can't recall what that point was.
No worries. Give some thought to it, Chris. And while you're thinking about it, I'll ask.
Okay.
I'll ask Greg. Yeah. The winner, the $50 million winner of the X Prize for carbon removal, was actually an alkalinity solution, where they proposed to sprinkle rock dust over the soils in India. I'd love to get your thoughts, Greg, on its effectiveness and any side effects that you might thought, or what your experience was with that, and what your thoughts are on META.
Yeah. Yeah, well, that's a sort of a variant on what we're doing in the ocean. Again, these rocks or alkaline sources are reactive with CO2 and water. And so, yeah, why not do that on land just as we're trying to do in the ocean? So that makes perfect sense. Again, you do have to be careful about the environment and there are the side effects of doing that. Are there any negative effects from that? And presumably they're monitoring the impacts of doing this on land. Um, I'd also say that it really, at the end of the day, could be largely an ocean alkalization process because uh, the weathering of this material on land can produce solid carbonates. So that's one way of storing the carbon, or one transformation is that you put this stuff on the land and it actually mineralizes or carbonizes the carbon so that it resides in the soil as a carbonate, calcium carbonate, magnesium carbonate, whatever. However, in moist environments like soils often are, there is the formation of bicarbonate and carbonate ions, alkalinity in the soil water. And ultimately, that will drain into drainages, into rivers, and ultimately that will wind up in the ocean. So I'm kind of curious what fraction of this enhanced rock weathering on land actually becomes ocean alkalization, although it's not going to enhance ocean's uptake of CO2. In that case, it's simply a medium for storing the carbon in the form of dissolved bicarbonate and carbonate ions in the ocean that have been previously captured on land from the atmosphere.
I've heard
So go
I've heard
ahead.
that's about 100,000 years for the calcium bicarbonate timescale in the ocean. Is that
Yes, it doesn't stay. Another aspect I should mention here is that bicarbonate and carbonate ions in the ocean storage as carbon is not forever. In the long time scale, ultimately that carbon is lost, and it's lost in two ways. One, about half of it is lost as calcium carbonate. It precipitates out of the ocean as calcium carbonate. It sediments to the bottom. Ultimately, it gets buried, and ultimately it enters into the geologic carbon cycle as calcium carbonate. The other half of the carbon is converted to CO2, and that is simply returned then to the atmosphere or the ocean atmosphere system. So on that time scale, the storage efficiency is only half as efficient as it is in sort of the present day, the next 10,000 years, et cetera, where almost all of the carbon that we're converting is stored as bicarbonate and carbonate ions. But in the long time frame, we have to be honest that only half of that's going to be permanently stored. The other half will be released as CO2. Now,
interesting?
that aspect is not in the current carbon market valuation, but in the long grand scheme of things, we have to be honest that that's what happens.
Yeah. Do you have any thoughts on the long-term potentiality and scaling limitations for such a terrestrial agricultural application of alkalinity and or high alkaline rocks? And do you see that at the moment, based on your analysis, do you think this terrestrial approach has cost advantages over ocean alkalinity that you're working on?
Yeah, I'm not familiar with the economics there. They have a transportation and source problem just like we do, so they're subject to those same concerns. I will say that if they're making calcium carbonate or they're making carbonate minerals, our our process is actually more efficient. We can, per mole of alkalinity, we generate more carbon storage than they can because we're making not only some carbonate ion, but also predominantly bicarbonate ion, which is from an alkaline storage point of view is much more efficient. It only takes 1 mole of alkalinity to store it as bicarbonate, whereas it takes 2 moles to store it as carbonate ion or as a solid carbonate mineral. So there's an advantage there to OAE, but in that respect. But yeah, in terms of comparing the two, my feeling is that we need both. Let's do both, and let's not quibble over who's the winner here. Let's both are part of what nature's going to do anyway, and let's see how much we can enhance what's going to happen anyway.
Yes, that's a great point, Greg. We need all 8 cylinders firing in order to actually get this thing off the ground in terms of carbon removal. Dennis and then Peter.
Right. Yeah, I'd like to return to the comments you made about the income from the voluntary carbon market. I chair the board of a large consortium of organizations implementing massive programs on land restoration. It's called the Global Evergreening Alliance, and we work with hundreds of thousands of smallholders in Africa and Asia, expanding their agroforestry and forestry. And John Dixon is here with us. He's on the board of this organization. Now, this is financed by upfront payments of companies, projects that we're getting about $6 to $10 per ton of CO2 absorbed by these managed ecosystems. So I was wondering what may be the range of return per ton that Planetary Technologies is able to attract, because obviously $6 to $10 per ton is pretty low for what services are required, and I wonder if you're doing better than that and are able to capture larger prices per ton for your work.
Yeah, well, typically the price we're getting is, hundreds to $1,000 a ton kind of thing. And we might be able to, command that kind of value because we argue that our storage is longer than would be in the biosphere. That's one thing that people are looking for is durability of storage. And so that's one advantage that we have, that we do offer longer term storage, and in many markets that's a big deal. Durability is important, and people are willing to pay a premium for that.
Yeah.
So that maybe is the reason.
Very good, very good. That's fortunate. Just to follow up, do you have some active projects going, and where are they being implemented around the world?
I would say our lead place is in Halifax, Canada. Planetary is a Canadian company, and we've the X Prize demonstration that we did was based in Halifax. That's where we have the most experience and the longest running trial. We did a trial in the UK, in Cornwall, and that was actually our initial trial. It was a very small trial. We did encounter community headwinds there. There was some pushback for us doing it there, but the real reason we're not pursuing that right now, and probably won't pursue it, is again because of logistics of getting alkalinity to that particular location. It was a fairly remote location, and as we've learned, it just didn't make sense from an economic and from a carbon footprint point of view to try to transport material to that site. So there are other sites that are much more economic, Halifax being one, and that's one reason why we're focusing on Halifax. But we also have another active site in Virginia, in Norfolk, Virginia. And that came about because of a collaboration with the University of Maryland. They were interested in teaming up with a wastewater plant to conduct CDR research and development. They needed an industrial partner in this field, in which we we came on board to fill that role, although they are also partnering with the wastewater plant itself. So it's sort of a triple partnership here. We've done an initial trial last year, and we're gearing up to do another trial this year where we're adding alkalinity in the form of hydroxide into an existing wastewater treatment plant to perform CDR. This project is funded by NOAA. It's actually one of the first MCDR project, or at least OAE project, that was been funded by NOAA. So we're fortunate to have that support, although it remains to be seen how long that's going to last under the current regime.
Mm-hmm. Greg, what
So,
causes the
so far,
difference?
so good.
Yeah, what causes the difference in efficiency from one location to another? If you add a given amount of alkalinity, let's say in one outfall versus another outfall, why do you getting different efficiencies of carbon uptake?
Yeah, well, it will come down to, first of all, what are we using as a source of alkalinity? It depends a little bit on the alkalinity that you use. In terms of, tons of CDR per ton of alkalinity we add, that obviously it depends on the nature of the alkalinity, but I would say largely it depends on the oceanographic conditions. And again, it gets down to this air-sea gas exchange. If we are discharging into a very shallow, long-lived reservoir, then we've got a really good chance of a lot of equilibration happening before there's any chance of subduction of undersaturated water away from the atmosphere. So in those settings, we can have very high efficiency. And if we have a really good alkalinity source, we can be very efficient in terms of tons of CDR per ton of alkalinity we add, as opposed to another place where there might be very quick subduction of the water, or maybe the discharge of a wastewater plant or a cooling water plant is deeper, is into deeper water, where only a fraction of it actually gets to the surface, and there is a larger fraction that's subducted and isn't going to interact with the atmosphere right away. So those are the reasons why there's variability in efficiency in various geographic locations. And one does have to be a little careful about where you do this if you want to maximize that efficiency.
Makes sense. Before I call on John Dixon, I'll just conclude that actually that implies that cooling water outfalls would be attractive because those tend to be right near the surface, and thus you get the best air-sea gas exchange under those scenarios.
Plus, warmer water is buoyant, more buoyant than cold water, so it has a tendency to float on the surface. So maybe you've got an advantage there. So yeah, any sort of tricks like that where you can take advantage of long residence time at the surface in contact with the atmosphere is a big advantage.
I remember that the cooling water of the San Onofre nuclear power plant was one of the most attractive places for dolphins and fishes and all the rest. They loved it there. So life loves a gradient. Over to John and then Peter.
Thank you very much, Brian. And to build on your question, Greg, this was fascinating overview with science detail behind. I was just wondering about this location question, and my mind immediately went to the idea that in tropical higher temperature waters, chemical processes and air sea gas exchange would probably be higher than at Halifax and in Cornwall. So that was even notwithstanding the Gulf Stream off Cornwall. So I was wondering what your thoughts are about tropical areas, number one. Number two, you mentioned actually delivery feasibility and arrangements and costs. And I suppose that off Halifax, my mind immediately wondered if you were thinking about the fishing fleets out of Halifax as a delivery mechanism. And if so, might something like that work with smallholder fisher folk in the tropical regions?
Mhm. Well, it is a thought, and yeah, I would think ultimately OAE does have to go to the open ocean and not rely on just on coastal discharge. We're doing coastal discharge because logistically it's easy, it's permitted, and et cetera. So it's low-hanging fruit. But at the end of the day, I do think that we do have to get offshore and think about ways of deliberately alkalizing those, the open ocean. And certainly one way to do that would be to utilize infrastructure, boats that are already going out there and doing whatever they do. Could we load them up with some alkalinity that they could discharge? I think to do that, we'd have to convince them that it is an advantage for them to do that, that it's beneficial to the fish they're trying to catch, and it's not harmful to them. Maybe they can get an income from doing that. There's a lot of things I think that would have to be in place in order for that to happen, but it's an idea. Certainly, they go out with empty holds that they could have full of alkalinity. They could dump the alkalinity and then fill it up with fish. And if they could somehow get an income or perceive some sort of benefit for doing that, then that would be a good thing. Of course, we do need to prove that doing this in the open ocean is a net benefit and not a detriment. So there's some work that needs to be done there. But
what's the fish productivity impacts or effects of alkalinity work?
Well, there has been some study looking at the effects of alkalinity on juvenile fish. There's been a few studies, and so far they've been neutral to positive, as I recall. But clearly more work needs to be done there. But let's keep in mind that marine organisms live in an alkaline environment already, so they're already adapted to significant alkalinity. And given that the rapid dilution of the alkalinity we're delivering, it quickly becomes actually unmeasurable, like meters to very near where we're discharging. It dilutes very rapidly to the point where you can't even chemically sense that we've added anything to the ocean. So I think there's a good chance that there's not much of an impact, but clearly we need to prove that that's the case, and especially in the open ocean.
Right. One question for clarification, Greg. When you add OH, for example, to the ocean, does the mechanism work by improving the efficiency, say, of the calcium ions in capturing bicarbonate, capturing two carbonic acid molecules, or how does that work?
Well, by adding OH, you shift the pH, you elevate the pH, you lessen the acidity, you consume acidity. And it is a little complicated, but the carbon in seawater is in three main reservoirs. It's in molecular CO2, it's in bicarbonate and carbonate. And as you elevate the pH, you shift the relative abundances of those three groups. And by elevating the pH, you transform some of that CO2 that was originally residing as CO2 into bicarbonate, and you shift a little bit of the bicarbonate into the carbonate. So the net effect is you reduce the molecular CO2 concentration in that seawater by elevating the pH. And what that does is either it reduces the excess CO2 that otherwise would emit to the atmosphere, or it undersaturates the seawater so that you get a net flux of CO2 from the atmosphere into the ocean. And that's where you get the net consumption. So that's the sort of the chemical mechanism of what we're trying to do here, is to shift the balance of carbon more toward bicarbonate and carbonate, undersaturate, reduce that CO2, either to reduce emissions from the ocean where we're operating, or to increase the flux into the ocean.
Very good. That makes sense. Peter, then Robert. And we're getting close to the end of our call, but Peter, go ahead.
Oh, yeah, thanks. Greg, two questions. One is, what's the reference number of tons of CO2 per ton of alkalinity? I always think of 1.4, which is for limestone. Is that pretty close?
Well, it of course will vary very much depending on the nature of your alkalinity. If you're using calcium hydroxide, it's different from using magnesium hydroxide because of the molecular weights. There's more or less alkalinity depending on the molecular weight of what you're working with. But as a general rule of thumb, the stuff we're working with you can get approximately 1 ton of CO2 per ton of feed that we're using. Just
Wow,
as
okay,
a
that's a lot.
general rule, it's about 1 to 1. Now it's going to be more or less depending on where you do this, the efficiencies, the chemical makeup, etc. That's
Great.
that's that's the rough
Yeah,
idea.
great. Okay, 1 to 1, that's better than I thought. That's great. The other question is, at the end of ice ages, what has the carbonate turned into CO2 so suddenly? Do you know about
Well,
that?
the whole glacial, interglacial carbon phenomena is it's really fascinating. It's fascinated me for a long time. I'm not sure anyone yet knows the full story as to why that happens, but clearly there is ocean plays a big role in that. How does that happen? I think is still a big question. And
Do you have a
I don't
favorite
know that
theory?
I'm the guy to answer that, but was there something specific that you wanted me to comment on, or just generally
Oh,
how that?
just but I don't even have, if someone asks me that question, I say, well, I don't know, maybe something changes the pH, but I have no idea. I just figure you're much more of
Yeah,
a
well, there's
chemist than I am, so you must
yeah,
have a favorite
it's a
theory.
yeah, really fascinating question. A lot of people have spent a lot of time trying to answer it. I think the answer so far is that it's not one thing, it's sort of multiple things. It's thermally related. It is related to ocean chemistry because, as you recall, if you withdraw pure water out of the ocean and form all these ice caps, you're really concentrating the chemistry. You're increasing the alkalinity. You're doing you're really concentrating the chemistry there. So that's another factor. People have argued that there were coral reefs that affected the carbon cycle back then, and then they got inundated, and that changed the carbon cycle. The land biology part of this, the idea is that, well, you really reduce photosynthesis on land during ice ages, and somehow all that organic matter got stored in the ocean or somewhere, and then suddenly it got re-released when it warmed up. So there's whole variety of mechanisms there. And I think the current thinking is that there were multiple things going on that caused both the drawdown and the subsequent interglacier buildup. What fascinates me is that when you look at the ice core record of this, how consistent the lows and the highs are. If this was a
Yes.
complicated system, you would not expect each ice age to be at 180, 190 ppm, and each interglacial being at 280. That does not make sense to me. If you have a complex system, each one of those parts could play a different role in each one of those glacial cycles. You're telling me that they all played sort of equal role in order to get that perfect range. That doesn't make sense to me. That tells me that there was one or a very few number of mechanisms responsible.
Yeah.
My theory was that it's all related to ocean temperature, that it's all thermal. As you cool the ocean, you absorb CO2. As you heat it, you exclude CO2. I don't think it's quite that simple, but I think the thermal part of this has been underestimated, but that's just my hypothesis.
Yeah, along those lines, when the ocean is warmed, you cut off the supply of nutrients, which you alluded to earlier. So, to the extent that the biological pump is involved in CO2 equilibration, the availability of that biological pump is strongly related to temperature. And with cooler ocean temperatures, you get better overturning circulation throughout the
Less
world.
less stratification, is that
Yes.
as you're saying, more vertical mixing. So you get these nutrients coming back right away. And so that's an argument for the biological pump playing a big role. My reading of the literature is that, okay, then maybe that could account for a third of the drawdown, but not for all of it. But clearly no one's proved it one way or the other. So it's
Right.
still an open story. And it's really kind of embarrassing that the global carbon cycle people can't explain this in an effective way, and it really is embarrassing. And I would love to know the real story.
Yeah, given that there's 40 times as
I have
much
to go. So
CO2 in the ocean than there is on land, I think there's a strong possibility that they may have underestimated that one third. Anyway, we're almost at time, so I'm going to ask Robert,
yeah.
Chris, and Chris Vivian to be very quick with their questions, and then we'll wrap this up. So, Robert, whoops, you're muted, and Chris, you can be on deck.
Okay. My question was
Right. Okay, let me go.
Let's
So
go
okay,
with Chris
Robert's
Vivian first, and then back to you, Robert. Thanks.
Okay. Greg, I had a concept that we could, if we had a suitable process that on ships, you could take the CO2 out of their stack emissions, convert it into bicarbonate and carbonate, and discharge it straight into the sea. So that would make shipping net negative in practice if you could come up with a system. The only other problem would be, of course, MRV would be a total nightmare, if not impossible. And also, you might need to control it in some way, because otherwise you might be putting too much alkalinity into some places that might be a problem, to put it wild. So controlling it in a way that would put the stuff into the right place might be feasible. But I haven't come up with any system that could actually do that, I don't think.
Well, Calcarea, I think a company called Calcarea, Jess Atkins at Caltech, has patented and is pursuing an onboard wet limestone scrubbing technology for ships, specifically for what you're talking about. They wet limestone scrub the flue gas and convert that carbonate into bicarbonate and carbonate ions in solution and
Right.
dump that out into the ocean. And as you know, there was this recent ruling that shipping is going to have to reduce its carbon emissions. So I imagine that this company and others are going to be in a very good position to use that technology.
There are some other processes the ships are using, but they involve producing solid waste that they have to take back to shore and discharge, which is rather more clumsy.
Greg, do you have any sense for the fraction of the stack CO2 that they can actually draw down with this method?
Well, they've done this on land. This method is, in fact, I was one of the inventors of this wet limestone scrubbing on land. We were going to do it in power plants where you, instead of doing CCS, you do just simply wet limestone scrubbing of the stack gas. Some people have taken this and done some pilot studies in actual power plants, and they get something like 50 to 80% efficient reduction in emissions. So, it is possible to do some significant, and you're not going to get 100%, but at least some emissions reduction here. And so, and it is adding alkalinity to the ocean, but keep in mind, in this case, it's already carbonated, so that you're not going to do any additional CO2 drawdown by adding this alkalinity. The alkalinity is already carbonated. You've already added that carbon from the emissions from the smokestack, and all you're doing is adding this alkalinity as a storage medium for the carbon that you captured from the stack gas. And plus, you're also elevating pH. So there is a marine benefit when you add alkalinity. You elevate pH. So it is still an antacid, but it's not going to do any additional carbon dioxide removal.
Perhaps a reduced emission. Robert, Chris, a quick question, and then Jonathan will wrap us up.
Okay, it was just really an observation that you mentioned earlier, Greg, that if I got this correct, that the materials handling was sort of 1-to-1 in terms of the amount of carbon that was sequestered. I know I've not looked at marine CDR, but I did look at enhanced weathering on land, which is, as I understand it, a very similar chemical process. And assuming you're using pure chemicals, the materials handling measured in terms of units of CO2 was 9-to-1. So for every ton of CO2 that you're capturing, you've got to handle 9 tons of materials.
On land.
Sorry?
On land.
On land, yes, on land. And I just found it quite interesting that there was such a massive difference, an order of magnitude difference, when you did it in the ocean. I don't know whether you have any thoughts on that or observations on that.
Well, first off, this enhanced rock weathering on land, they're just simply using rocks or existing minerals. And a lot of those are silicates, it could be carbonates as well. They're slow reacting. They're just not very efficient. And so, yeah, you're not going to get a whole lot of carbonation in a given unit of time. So I'm not surprised that it's going to be less efficient. In our case, we're using materials that are refined but are still waste. In other words, they were maybe part of a line production, but they were off spec, or there's something that wasn't up to spec, so they couldn't actually sell it on the line market. But it's still very useful for us. But in any case, it's much purer and it's way more reactive. So on a ton CDR per ton of feed, we're going to be more efficient there. But it is going to cost us more because, well, potentially it'll cost us more depending on what we have to pay the provider. In some cases, it can be free, but then we have transportation costs, et cetera. But in terms of material handling, the material we're using, I think, per ton should be more efficient than those people that are using rocks to do the same thing.
And last detail, if you're talking about scaling this to sequester gigatons of CO2, are the precursors available in sufficient quantity?
Well, certainly not. I don't believe waste material is available. And that's why I said up front, in the long run here, we're going to have to figure out green, cost-effective ways of generating this alkalinity. And I originally got into this story by looking at an electrogeochemical way of doing that, making green alkalinity using green electricity and electrochemistry. It is possible to do. I and others have done it. You can make magnesium hydroxide, calcium hydroxide, et cetera, from rocks. The problem there is the cost of doing that, and right now it's prohibitive. But I think in the long run, there are some breakthroughs that are happening in electrochemistry in this area that I think will bring down the cost and ultimately could provide the kind of substrate we need for large-scale OAE. There are also things going on in the thermochemical area. In other words, like calcination, things like that. There are green ways of doing that are being developed. That's another way that we could come up with converting rocks into very reactive alkalinity at a low cost green way. But that's some distance off as well.
Wonderful. Jonathan?
Thanks. Mankind is very good at disrupting things, or to put it more crudely, to blow things up. Most of mining that we look at is blowing up or disrupting rock formations on land. And for the purposes we've been talking about, bringing them to the ocean and dumping them in. But are there rock formations already under the ocean water that if we were to disrupt them and increase their surface area, they would operate as for the purposes you're after?
Yes, in theory. Yeah, there's ocean touches a lot of rock. And so if there's some way we can go in and disrupt that surface and make a higher surface area, fresh surface area exposed to seawater, yes, in theory, we'll be able to accelerate this rock weathering. But on the other hand, you've got to think of the environmental impacts of doing that. There are critters that are living on those rocks, and there's whole food webs that are associated with that area. And so it would seem very disruptive to existing ecosystems if we were to do that. But in theory, yes, if there's some way we can increase the surface area, fresh surface area of rocks, then yes, we can accelerate this natural rock weathering process in the ocean.
Ocean mining is exploding whether we want it or not. So, I mean, right?
Good question. Good question. That's great. Well, Greg, this has been fascinating. Thank you for, on an impromptu level, having a conversation with us here at the Healthy Planet Action Coalition to really understand how adding alkalinity to the surface ocean can have transformative effects in terms of drawing down our CO2. It's really great to connect again. Looking forward to staying in closer touch as we go forward and really identifying approaches that we can all use to get all eight cylinders, so to speak, firing on this question of sustainable carbon removal. So thank you so much today.
Okay,
Thank
great.
you.
Well, nice talking with you. Great questions. And yeah, do keep in touch. And any breakthroughs, let me know.
Will do. I'll be in touch shortly. Very good. Thanks,
All right.
everyone. Have a
Bye,
good
guys.
day. Bye.
All right, I'll close it off. Thanks, Brian.
Good call today. Thank you, Robbie.
Okay, all right, bye.
Bye.